Thank you very much. So I'm Gergely Czél from Budapest, Budapest University of Technology and Economics, and as Jentil already mentioned, I would like to talk today about alternative specimens which can be used for measuring the UD tensile strengths of fiber reinforced composites. And these should make a bit of a progress if we compare them to existing standards. So the simplest test we can do on a composite panel is the UD tensile test. And we tend to do it all the time, and we tend to avoid any other tests if we can. But still, this simple test is a challenge because we have some intrinsic artifacts and some difficulties in executing them. So let's have a look at. Doesn't quite seem to work. Now it does. Okay, so let's have a quick introduction into composites. LEVE obviously is a cycling cycle, and everybody who ever tried a carbon fiber bike frame can confirm that fiber reinforced composites are stiff and strong, and they are lightweight as well. So we really like them. But unfortunately, their failure is usually catastrophic. So I'm sure that we don't want to be involved in accidents when, for example, bike frames or forks split or snap. And to avoid these incidents, we really need to test our materials. We should try to gain more confidence in our models, which are alternative to models for isotropic and homogeneous materials, are usually much more complex and complicated, and therefore maybe a bit less reliable, and also we have much less experience. So there is no such historic experience as we do have in metals, for example, steel and aluminum. So therefore, testing composite materials is of key interest to modelers and designers. And on the other hand, the combinations of existing fibers and matrix materials is nearly infinite. So we are in a bit of a trouble, because even if we just look at the most widespread composite types, we are approaching hundreds of different fiber matrix combinations, and testing all these is probably not feasible from many aspects. So we need to be very clever, and we need to design our tests in a wise way to limit cost and time and effort contributed to testing composites, but still gain reliable results from the test. Otherwise, it's all useless. So characterization of UD composites is quite challenging because our material is highly anisotropic. So the default approach to test homogeneous materials, when we have a wider section which is clamped and a narrower section where we expect the failure, simply doesn't work. So since our material is anisotropic, so the fibers are all aligned with the loading direction, the widen or the wider parts of the gripping sections can simply split. We can have a fracture running along the fibers, and we just lose the wider parts, which would make the clamping better, or which could sort out the immediate problem we can have by having the failure of the specimen not where we would like it to happen. So what we can do is to use parallel edge specimens. And in this case, we normally use bonded, adhesively bonded end tabs on our specimens, which we can see here. And there are ways of designing these end tabs and applying the end tabs, but the common target is to reduce the stress concentrations, which would immediately arise at the tips of these end tabs. And let's have a closer look at the stresses near the end of the specimen and the edge of the end tabs. So our main active load is this tensile load on the specimen. And then let's assume that the grip is fixed so that the end tabs are held in place. And what we do essentially is to transfer these tensile loads to our specimen through shear stresses arising at the bond line between the tabs and the specimens. And this on its own will result in a combined normal and shear stress state at the tip of the end tabs. So people, and also myself, I thought that the compressive stresses coming from the gripping force are the most detrimental effect to the specimens, but actually not. This combined shear and normal stresses are the more problematic issues. But of course, on top of this, we still have the normal forces from the grip faces. But this usually actually helps when it comes to this debonding, for example, between the end tabs and the specimens. A little bit of normal force, compressive force can even help. Okay, this is not usually just a little bit, because it's actually in some times, or maybe many times, it's a higher force than the actual active force, the tensile force, because of the wedge angle of the grips. So it's a quite high force, but not that harmful to our specimens. But on the other hand, this shear and normal forces or stresses are compromising the final failure of our specimens. So we normally have failure near the end tabs. So what can we do with this? Because the test is so simple. We just need to transfer the stress, the normal stress, to the specimen, and then watch at which force or displacement or strain or stress it fails. But we fail to do this right at the beginning, because we cannot transfer the stress, this normal stress, to the specimen properly, because it's not uniform. So there are high peaks towards the ends of the specimens in the arising stresses. So what we can do is to try to reduce or eliminate these effects. And one way is to design the end tabs so that they lose stiffness towards their tips. So they get less stiff towards their tip. And this is the standard design, or one of the standard design. of the end tabs, so that we have a taper, a shallow angle taper. The recommended angles are below 10%, and this way we have a section of the specimen where we have less and less added stiffness coming from the end tabs, and finally it fades away. So in a way it distributes the stress concentrations. It sounds funny. So the stress concentration, the word concentration is right the opposite of distributing. But anyway, we try to smear out a little bit these stress concentrations. But unfortunately, there might be debonding towards the tips, and there might be some issues with this design. And we need to say straight away that it's not possible to fully eliminate these stress concentrations using this approach. We can reduce, but we cannot eliminate this way. And then the other common design is when we have the end tabs completely inside the grips, and we don't bother with the taper, which is actually quite hard to make, manufacture, fabricate. We just use a thick but controlled thickness layer of adhesive, which is quite ductile, and this way we let the adhesive layer damage, and we may even allow for a little bit of debonding towards the tip of the end tab or the edge of the end tab. And we don't bother because we know that the bond length is way longer than what is required to transfer the stress based on the shear strength of the adhesive. And then we let the interface damage a little bit, and this results in knockdown of the very high stress peaks near the edge of the end tab. But again, it's possible to reduce the stress concentrations this way, but not possible to fully eliminate. Then we can even taper the specimen, the end of the specimen, by ply drops or ply insertions. I will talk a bit more about this later. Then we can use special shapes for the whole specimens, just like the one Rajnish has shown, the butterfly shaped specimens. Also, we can design special shapes for the end tabs, just like arrow shapes. I will elaborate a little bit more on this as well. And finally, the main topic of my talk will be the use of continuous end tabs or protective layers on our specimens, and we can also call this whole concept hybrid composite specimens, test specimens. So first, let's look at these tapered end specimens. So what happens is that there are some plies inserted towards the ends of the specimen to make it thicker. But one key aspect is that they aim at a smooth transition of thickness between the gauge length of the specimen and the clamping region. And key aspect is that the plies on the surface, actually all the plies of the continuous section are kept continuous towards the gripping section. So there are no discontinuities in the plies which are constituting the gauge section of the specimen. And of course, they are continuous on the surface as well. And another key feature is that these infill plies are chamfered, so that there are not too big resin pockets at their end, which can reduce the possibility of delaminations starting from those resin pockets. So this is a clever concept. The only issue is that, okay, there might be more than one. So one is that the gripping sections still need to be protected. Otherwise, the sharp nails of the grips could damage the useful plies, the continuous plies, and could cause premature failure. And the other one is that manufacturing is really not simple. So to do this, we actually need to put the same thickness plies to the continuous section, the gauge section, like space holders, and then we scrap that one. We cure the whole thing, but we only use part of it, and so it's really an advanced technique, and it's complicated, but might not be feasible on at an industrial scale, let's say. But nevertheless, gauge section failures were reported with this approach, which was really promising. So then another way to reduce the stress concentrations is to taper the specimen, not only in one direction but two directions. So normally we taper in the through thickness direction by tapering the end tabs. As these specimens also have tapered end tabs, might be just visible on the side view, but also we can taper in the width direction by applying these very large radii on the side of the specimens. And this way we can have very smooth transitions in two directions towards the gauge section of our specimens. But again, compared to the standard specimen geometry, this is rather difficult to manufacture. But otherwise, it was reported that much higher failure strains can be achieved using these specimens than the standard ones. And there is one more issue with this technique, is that the stress volume is not very well defined. So we can consider that part of this increased width zone is also stressed, and there might be critical clusters developing in this volume as well. But we need to reduce the strength, the average strength. So we can have different approaches to analyze the stresses and the volumes of the specimens, but this is just a little bit of a complication which can be dealt with. Then we can use special arrow-shaped end tabs, which are not cut perpendicular to the side of the specimen, but under given angles. And actually this angle is a parameter of this tab geometry. And the key idea here is to have a longer edge along which the stress concentrations arise. So in a way, we can extend, or we can make the affected area larger by applying these arrow-shaped end tabs, and we can smear out the stress concentrations over a slightly larger area. And of course, it is designed in a clever way so that the gauge length is uniform, so you can spot a fiber and you can measure if these two angles are the same. All these lengths will be exactly the same, and also it is symmetric also to the mid axis of the specimen and the mid plane of the specimen as well. So there are no unexpected distortions or any naughty effects arising during the test. On the other hand, if we have a fixed depth of the grip, we lose a little bit of the gripping area because of this cutout and this part. So this could be a limiting factor, but I think in most of the cases it is not a big issue. But again, manufacturing, fabrication of the specimens is slightly more difficult than the standard one. So we need a CNC cutter, usually water jet cutting, to make our end tabs. On the other hand, quite promising results are being generated with this approach. It has not been published yet. So I'm referring to Jentil's slides here. But it seems that significantly higher failure strains can be achieved with these arrow-shaped end tabs than with standard specimens. And now, let me give you a short introduction to pseudoductile hybrid laminates, because that was the starting point to the development of the interlaminar hybrid composite specimens, which I am going to propose for accurate testing of UD fiber reinforced laminates. So we already agreed that high performance composites are stiff and strong, but their failure is sudden and can be catastrophic. And to address this, pseudoductility can be of interest, and it can change the design approach and give the designers major benefits. And so far, with thin ply carbon and standard thickness S-class plies, excellent pseudoductility was demonstrated. And let me quickly show the phenomenon here, so that if we have a hybrid composite where all the layers are reasonably thick and the high elongation layers will not break when the low elongation layers break, this is what we can call a properly designed conventional hybrid composite. Then we have a major load drop when the low elongation component, let's say the carbon epoxy in a glass carbon hybrid composite, breaks. So we have a load drop, and then the high elongation layers, namely the glass epoxy layers, can take the load and give a further rise to the stress strain graph. But if we have thin plies in our hybrid composite, thin low elongation plies, we can have fragmentation, and that can provide us with a stable plateau in the stress strain response, and then we can further exploit the strengths of the high elongation layers. And this is what we call pseudoductility. So it is not real ductility at all, because all fibers and all matrix materials are brittle in our system, although epoxy at the micro scale might be ductile, especially in shear, but that's another issue. But all our fibers are perfectly brittle, but still with a controlled failure and a designed architecture, we can get something like ductility, let's say. And so as I mentioned, our main mechanisms are fragmentation of the low elongation plies and stable delamination between the low and high elongation plies. And let me just quickly show in this short video what happens. So you can see through the transparent glass epoxy layers that the carbon fiber breaks at several locations along our composite, and then these lighter spots or lines indicate the local delamination around the carbon epoxy layer fractures. And this concept was first shown for glass and carbon hybrids in a unidirectional structure. Then we extended the concept to two different carbon fibers, intermediate and high modulus carbon. We hybridized. These were also unidirectional. Then we made a quasi-isotropic version where obviously the initial modulus was much lower, about 1/3, as we expected, but we used ultra-high modulus fibers to somehow boost it a little bit, and we still got pseudoductile behavior. And we also included a structural aluminum response for comparison. So even with the quasi-isotropic pseudoductile hybrids, we are stiffer and slightly stronger as well. Of course, the final failure strain is nowhere near aluminum, but that's the state of the art so far. Okay, so concept works for multiple pairs of materials or multiple structures. But what we have seen during the test when we failed to produce ductility is that when we have a single delamination, we can very accurately monitor the failure strain of the low strain component in our hybrid, meaning the carbon epoxy ply. And so we thought, why shouldn't we exploit this for developing a new test specimen, a new test method for unidirectional, not hybrid, but monolithic composites to determine the failure strain in a better way than what we do according to the standards. Yes, and as we have seen during the video, or we can see on this little picture, if we put the glass epoxy plies towards the outside of the composite, the hybrid, we can actually detect the damage occurring inside the laminate by our naked eyes. It can be either multiple fractures and local delamination, or a single fracture and full delamination. Doesn't matter what the damage mode is, we can see. And this is a very straightforward visual confirmation of what is happening. If we would have a black laminate which disappears from the grips, that's something quite hard to interpret. But what we have is something else. And also we developed this concept, the hybrid composites, into an overload sensor, which was patented in the UK. So if we simply stick a piece of glass and carbon composite on a substrate and we put it under tensile load, according to the failure strain of the thin carbon layer, we can tell at which strain did we stop with loading the composite part. And this was again just something we discovered on the way when we wanted to develop pseudoductile fragmenting hybrid composites. So our concept for the test specimens for measuring the failure strain of UD composites is a delaminating hybrid composite, not a fragmenting one, but a delaminating one. So we need to design the specimens so that we will get delamination at a given load or given strain, which hopefully corresponds to the real failure strain of the carbon epoxy layer. Not earlier and not later. Jentil already mentioned that if we would have a strong hybrid effect, we may have failure later than we should. If we have premature failure due to stress concentrations or any other artifacts, we would have early failure. So we want to catch the real failure strain of our material. So there are some simple design equations. One is that we want to keep the glass layers intact when the carbon layer fractures. It is for the stability of the test, for good detection of the fracture point, and so on. It's actually mainly for convenience. So we could even get good results if we make sure that it is not the glass plies which trigger failure, but if we fail the carbon and the glass fails immediately after, that could still be fine. But it's hard to make sure which layer we had the initiation of the final failure. So it's best to keep the glass layer intact, because in this case we can make sure that this was the carbon layer which initiated final fracture. So that is the simple equation to make sure. And these are just the elastic moduli of the layers and the strengths of the carbon layer and the layer thicknesses. Nothing really complicated. Also, we can formulate this to have the minimum thickness of these protective layers if we know the strengths or the failure strain of the components. It's actually based on the failure strains, which we can just use the fiber datasheet values as a first estimation. I usually do that. And if we want to go further, of course, we can characterize the available materials further. Okay, and then this is the more tricky one. We need to make sure that the system will delaminate when we have the first fracture in the carbon layer. So for this, we need to make sure that the energy released at the fracture of the carbon epoxy is higher than the fracture toughness of the interface or the hybrid. And here you can have the annotations for reference. And Jentil already touched on these graphs. These are actually numerical models to prove that we do not have stress concentrations at all in the carbon layer if we use the glass epoxy layers on top of them. And why is this? It's because we have a very strong stress concentration, but in the glass layer, which has a higher failure strain, so it will not fail at loads or strains we want the carbon fiber to fail. So we overload the glass, but it can take it, no problem. On the other hand, the carbon layer, which is between the dashed and the solid line, doesn't have any stress concentrations. And if you plot along a path, so it's across the thickness, the longitudinal strains, you can see that yes, at the surface of the specimen we have very high strains, but glass can actually go up to 4% strain, especially if it's very local, no problem, can go up to 4.5%, a good S glass. And then it drops down to even below the average far field strain in the carbon. So it's actually less likely that we have the failure near the tabs because of this tricky stress concentration and distribution near the tabs. So we are saved from this problem. Also, if we plot in the longitudinal direction, the the stresses at, the strains at the glass surface and the carbon midplane, we can see that this high peak is absent completely in the carbon, which is of interest for us for developing the test method. So we can conclude that it is possible to fully eliminate the stress concentrations if we are using these full protective layers on our specimen. Few words about manufacturing the specimens. And the key point here is to convince you that it's not more expensive or difficult or complicated than making a normal specimen. So what we use so far are pre-preg plies of glass and carbon epoxy, and we simply stack them together in one go. So we co-cure the protective layers with the carbon epoxy layers in one go in an autoclave, and this, at least it is my opinion, that it's simpler than bonding or retrofit the end tabs even on the standard specimens. So sticking 10 plies instead of 5 together probably is easier than bonding the end tabs afterwards to the laminate. But of course you can argue with this. And yes, it is more material consumed because we have a full cover of glass epoxy on our specimens. And I need to admit that it does matter what kind of what kind of glass we are using. So we recommend to use S glass, which has high strength and high strain. And the price of this material is approaching the price of carbon fiber epoxy, unfortunately. And let me just show the main difference. So with a monolithic specimen, there is an explosive failure. The specimen basically disappears from the gauge section. We cannot see the position, nothing. But with a hybrid specimen, we can see the position of the failure, and we can have the specimen in one piece. We can take it out from the grip. We can open up. We can even observe or try to do microscopy if needed. So the end result is more straightforward to analyze. And what we do in terms of test setup is really standard. Just a tensile test machine with a video extensometer. Could be a DIC system or could be a dedicated extensometer, which is video based. And so it is really nothing special. And as I mentioned, we don't have end tabs. We just clip the specimen, and we tend to use sandpaper at the end of the specimens because we have mechanical wedge grips, which have quite sharp and quite deep nails. So it would penetrate in the specimen quite deep enough, maybe to compromise the strength of the glass layers, the protective layers. But just using the sandpaper, it distributes this aggressive effect, and it stops these nails penetrate too deep in the specimen surface at the grips. And what we get as a result is these type of graphs with a clear low drop, and this corresponds to the failure strain of the carbon epoxy layer. And this slide is designed to show that we had 5 different configurations, even with E-glass protective layers, and then S-glass protective layers, different number of carbon fibers of the same type, with and without end tabs, and we've got consistently the same failure strain for the same carbon epoxy material. And yes, it was quite simple to determine the strains at which the carbon epoxy failed just by looking at the test graphs. And you can also see visually where did the carbon epoxy layer fail in the specimen. So I think it's reasonably convenient. And yes, we've got consistent gauge section failures. And we were not shocked that some of them were close to the grips, because statistically, there is a chance that we must have some quite close to the edge of the gripping regions. It wasn't under, just close enough, but we would have been surprised if we don't have any of these. Unless our material is so bad that it has many defects in the gauge section. But even if there are strong defects, some could be closer to the edge of the grips. So statistically, it's okay to have some fractures near the grips. But as a downside of this technique, we cannot calculate the strength of the specimens immediately. We need to back calculate it from the failure strain, which can be measured accurately, preferably with a video extensometer or maybe a bonded on electronic strain gauge. But the strengths, we need to rely on a reasonable modulus of the specimen, which can be measured separately on monolithic specimens. And again, this is a problem because we need to test the normal specimens as well. Or we are simply happy with the failure strains. And actually, in many cases for design, the engineers set a strain criteria. Hopefully I'm right. And so we may find that it's enough to determine the failure strain of the material. So what else did we do with this technique? We went and did a scaled test study, because we realized that this way we can get rid of any parasitic effects, no stress concentration, nothing. So we can determine the real failure strain of different size, different volume specimens in an accurate way, and then it's possible to come up with a good viable modulus. But there is one issue, that since we co-cure the layers at 130 degrees C, there are some thermal residual stresses arising in the specimen. So we need to consider this one. And just very quickly, I show a good approach to this. So we can use a multi-level rule of mixture. So first we can calculate the coefficient of thermal expansion of the two components of the hybrid, for the carbon epoxy and then for the gloss epoxy. And then we can use the same equations considering the stiffnesses of the constituents. So for coefficient of thermal expansion, we have an additional term in our rule of mixture, which is the stiffness of the constituent versus the composite, or the, let's say, the joint material, which in the next step will be the hybrid composite. So now we have fiber and epoxy, then we will have glass epoxy and carbon epoxy. So we apply the same style equations in a multiple way. And in this case, we also have the, you don't see my mouse, sorry. So we still have the stiffness term, and then the volume fraction is replaced by the thicknesses. But we can do this quite quickly and come up with a thermal expansion coefficient for the hybrid, and then we can straight away work out the equilibrium strain due to cooling down from 130 to, I don't know, room temperature. And then we can also correct our results. I just wanted to demonstrate that this is not rocket science, so anyone can do it with quite simple considerations. And then finally, we thought that, okay, these materials which we used so far, these TR30 and TC35 carbon fibers, especially in a thin prepreg made by a random Korean company, might not be of a lot of interest to people who we want to convince. So why not do some tests with commercial carbon fibers used by Boeing and Airbus and big companies. So we took Torres, T700 and T800 materials and Hexazium 7 carbon fibers, and I took the failure strain, the UD failure strain from the datasheet. That will be the darker blue columns, but this is for the fibers. Then datasheet values for the monolithic carbon epoxy composites. Then measured failure strains, our own measurements for monolithic specimens, and then measured values for the hybrid specimens. And for reference, I also included the volumes, which do not match too much, but you can at least see that there is no orders of magnitudes difference, where we would start to see effects due to the different volumes. So, okay, it's like 4 times, but not 100 times bigger for the 2 different specimens. And if you take a good look at the data, you can see that monolithic specimens gave quite a bit lower values than the hybrid specimens for the failure strain, but they were in line with datasheet values, so they are probably not that much corrupted. And with the hybrid specimens, we are actually approaching the fiber failure strains of the fiber, so the failure strains of the fibers reported in manufacturers' datasheets, which doesn't mean that it should be a baseline, because actually these fiber failure strains are based on impregnated tow tests, which I think is a little bit, let's say, not very well defined as a test. So we don't actually know how many fibers, how thick bundles, and how it was actually tested. But for sure, these are not individual fibers tested. So don't take it as a baseline. I just report here as something to compare my results against. But I think we are going to the right direction with these hybrid specimens. And yeah, a few key points as a summary. So there, the standard specimens are, yes, prone to stress concentrations, and there are different ways of trying to reduce this, but it's not possible to completely eliminate the stress concentrations by simply redesigning the tabs or the specimens. And usually doing this, it brings some extra complication into our preparation processes. On the other hand, continuous end tabs can fully eliminate the shear stress concentrations and provide consistent gauge section failures. Few points about design. So we have our formulae ready for designing the hybrid specimens, and at least to my judgment, it's not complicated to make them, not worse than making a standard specimen, and the evaluation effort is also reasonable. It's easy to detect the failure strain on the test graphs, and also the thermal residual strain correction can be done with reasonable effort. Okay, it's a complication, but can be handled. But there are still some challenges. Currently, the scope of this method is limited to prepreg-based composites with high strain S-class as a protective layer. But we are looking at commercially available high strain protective sheet materials, maybe in a cured form, not in a pre-pregged form, which we can bond to laminates afterwards, and also to eliminate the thermal residual stresses. It would be excellent to come up with a good method to bond the protective sheet and the laminate at room temperature. So that would be one less complication to the method. Thank you very much for listening.